Hi guys, I'm Mark Sarbunot from grade 12 STEM 2A. So for today's video, I'm discussing about electric flux. The concept of electric flux was described as quali- qualitatively, and now we treat electric field lines in a more quantitative way. Let's consider an electric field that is uniform in both magnitude and direction as shown in the figure. The field lines I are penetrate a rectangular surface of area A whose plane is oriented perpendicular to the field. Recall from the previous previous discussion that the number of lines per unit area, or in other words, the line density is proportional to the magnitude of the electric field. Therefore, the total number of lines penetrate in the surface is proportional to the product of E and A. This product of magnitude of electric field A and surface area perpendicular to the field is called the electric flux. Electric flux is proportional to the number of electric field lines penetrating some surface. Mathematically, it is the equation. So, paano yun sabihin? Pi sub E, that is that symbol this way. So, this symbol is called pi sub E. Okay. So, pi sub E equals to E and A, or you can call it as electric flux is equal to the product of electric field area and the SI unit of electric field and area. So the SI unit of electric flux is Newton meter squared per coulomb. So we have an example here. So what is the electric flux through a sphere that has a radius of 1 meter and carries a charge of +1 microcoulomb? So so this symbol is called microcoulomb. Okay. At its center. So for the solution, the magnitude the magnitude of the electric field 1 meter from this charge is found using the equation of E equal to K sub E multiplied to Q over R squared. So let's substitute the given to the formula. So first we have a Coulomb's constant 8.91 times 10 9 power Newton meters per coulomb squared, and for the charge, we have to convert it into SI unit column. So it became 1 times 10 and the negative 6 power column. And for the distance is we have to do to square it and then use our understanding and operation and scientific notation to solve this. So we will have an answer 8.99 times 10 cube Newton per coulomb. The field points radially outward and is therefore everywhere perpendicular to the surface of the sphere. The blocks to the sphere, whose surface area is 4 pi r squared. So we will use here the formula electric flux is equal to electric field multiplied to area. So substitute the value for the electric field 8.99 times 10 cube Newton coulomb and for the area is 4 pi times 1 squared, 1 squared. Then the area will become 12.6 meters squared. So parang sinolve mo dito. Yan. So we will have an answer 1.13 times 10 to the power to the fifth power Newton meter squared per coulomb. If the surface is in the surface under consideration is not perpendicular to the field, the flux through it must be less than that given the equation earlier. Um, we can understand this by considering the figure where the normal to the surface of area A is that an angle theta to, to the uniform electric field. Note that the number of lines that cross this area A is equal to the number that cross the area A prime, which is a projection of area A onto a plane oriented perpendicular to the field. From this figure, we see that the two areas are related by A prime is equal to A cosine theta. Because the flux through A equals the plus through A prime, we conclude that the flux through A is electric flux is equal to E times A prime equals to E A cosine theta. From this result, we see that the flux through the surface of a fixed area A has a maximum value E A when the surface is perpendicular to the field. When the normal to the surface is parallel to the field, that is theta is equal to 0 degree, and the flux is 0 when the surface is parallel to the field. When the normal to the surface is perpendicular to the field, that is angle is equal to 90 degrees. So we assume a uniform electric field in our previous example, but in more general situation, the electric field may vary over a surface. Therefore, our definition of flux given by equation electric flux is equal to Ea cosine theta has meaning only over a small element of area. Consider a general surface divided up into a large number of small elements. Each area of delta A, the variation of electric field over one element can be neglected if the element is sufficiently small. It is convenient to define a vector delta A sub I whose magnitude represents the area of 8 elements of the surface and whose direction is defined to be perpendicular to the surface element as shown in the figure. And the electric field E sub I of on the location of this element makes an angle theta sub I with a vector delta A sub I. So delta electric flux through this element is delta electric flux is equal to E sub I multiplied to the delta A sub I cosine theta. And it is equal to E sub I dot A sub I or E sub I times A sub I delta A sub I, where we have used the definition of the scalar product or the product of two vectors. By summing the contribution of all elements, we obtain the total flux to the surface shown in the figure. If we let the area of each element approach zero, then the number of elements approaches infinity, and the sum is replaced by an integral. Therefore, the general definition of electric flux is electric flux is equal to the limit of summation E sub I dot delta A sub I as delta A sub I approaches zero, which is equal to the integral surface of E delta A. In this equation, the integral of surface integral, which means it must be evaluated over the surface in question. So, in general, the value of electric flux depends both on the field pattern and on the surface. We are often interested in evaluating flux to a closed surface, which defined is one that divides the space into an outside so that one cannot move from one region to the other without crossing the surface. The surface of a sphere, for, ex, for, for example, is a closed surface. So consider the closed surface in the on this on this figure. The vector delta A sub I point in the different direction for the various surface elements, but at each point they are normal to the surface and by convention always point outward. So pag outward palabas. At element labeled 1, the field lines are crossing the surface from the inside to the outside and angle is less than 90 degrees. Hence, the flux through this element is positive. For element 2, the field lines graze the surface, which is it is perpendicular to the vector delta A sub 2. Thus, the angle is equal to 90 degrees, and therefore the flux is 0. For elements such as 3, where the field lines are crossing the surface from the outside to inside, which makes an angle less than 180 degrees but greater than 90 degrees, so therefore the flux is negative because cosine theta is negative. The net flux through the surface is proportional to the net number of lines leaving the surface. Uh, where it means the number leaving the surface minus the number entering the surface. If more lines are leaving than entering, therefore the net flux is positive. If the lines are entering than leaving, the net the net flux is negative. Using the uh, using the same the integral to represent an integral over a closed surface, we can write the net flux through a closed surface as net flux equal to contour integral of dA is equal to control integral of E sub En dA, where E sub n represents the component of electric field normal to the surface. If the field is normal to the surface at each point and constant in magnitude, the calculation is straightforward as it was in our previous example. That's all. Thank you.